Yeah. Yeah, it's another talk about integrability. Can I start? Yeah, great. So I'd like to start by thanking the organizer for inviting me, for giving me the opportunity to be here and to present my recent work, which was done in collaboration with Shota Komatsu and Pedro Vieira from Perimeter Institute. And the subject of my talk is closely related to what Romuald described. So he talked about this string vertex and so on. And we were also motivated by the very same kind of problem, more with the goal of applying it to the structure constant, which are the 3-point function. So this is roughly the plan or the goal of my talk, which is to let's take planar n equal to 4 superior mills. Let's take single trace operator and ask ourselves whether we can compute this well-known 3-point function. So as you know, thanks to conformal symmetry, if these operators are scalars, we just have a single structure which is fixed, entirely fixed in terms of the position of the operator and the scaling dimension. And so what is left to compute is essentially this number C, which is a function of the quantum number of the operator as well as the Taft coupling. Okay? And in the planar limit, we can think that we are, from the string theory side, just inserting some sort of vertex operators that correspond to creation of this operator with given quantum numbers computed on the sphere. Okay? So the question is, how do we compute this quantity at finite coupling? By this, I mean, how do we compute this quantity without relying on Feynman diagrams or worldsheet computation, which are typically difficult and also limited to a few order at weak coupling? And the answer was already given by Romuald. It is to use integrability. And this simplifies a lot because integrability, from a very pragmatic point of view, is like a way of getting control on the coupling constant. So once you understand properly the objects that you are computing in the integrable setup, the integrable equations, the kind of equations that Romuald have shown and so on, the S matrix, the kinematics, all of this includes information about the coupling, which is kind of given to us as soon as we have the right formulation. So the main question is, if we want to use integrability, is to first try to answer the question of what are we really computing from this point of view. And this is where we have to go to this, from the string theory point of view, we have to go to this massive description, this asymptotic description in terms of massive excitations that can scatter with each other with the factorized scattering and so on, and ask ourselves what this object wants to be from the point of view of this description. Okay? And the answer that I would like to give, the answer that we started to give with Pedro and Shota, is to use what we call a Bootstrap program, similar to the one that Romuald introduced, to which we add this Hexagon mention for reasons that will become clear soon. So I would like to say also that this is part of a bigger program, which many people are working on and have contributed to, which is to compute, in fact, all possible correlators of planar n equal to 4 superior mills, or if you prefer, trying to solve string theory in ADS 5 times S5 at 3 level on the sphere. So eventually, hopefully, this information will also allow us to describe loop effect. So it's not, I think it's an open question, at least. I don't know if this information, this planar information, is enough to create loop and so on, and to eventually perhaps define completely the theory in a 1/n expansion. This will have to be studied in more details. But at least there are significant evidence with the fact that the 2-point function problem, which is equivalent to the computation of scaling dimension, has been totally solved, and all the recent work and recent progress with 3-point function, there are evidence that perhaps we will be able in the near future to understand how to compute efficiently any sort of correlator on the sphere in this theory. So I mentioned the spectrum problem because it is also, with the history of this problem is coming some hint about the kind of procedure that we can follow. So here I have a big overlap with Romuald in the sense that essentially we have to go to this formulation, find a vacuum, which is like what I call BMN vacuum, which is this vacuum with a lot of scalar operator, complex scalar operator of the same type, which is BPS, which is very nice, and which supports this spin chain picture. So on top of this vacuum, we can put excitation, which is like generating the full spectrum of the theory, starting with a nice ground state. And by understanding the symmetry and the property of this vacuum, we can eventually move forward, understand the dynamics, and eventually write down a complete set of equations for the spectrum, which are summarized here. So, but the philosophy which is behind is not restricted to the spectrum, and in fact, you should think about this history as giving us, in a sense, a full infinite volume information about the theories that we cannot try to recycle for computing other quantity. So now the question is, what are these quantities that we might want to compute? What are these extra dynamical observables that want to exist in this theory on top of the BMN vacuum? And today I will show you one of them, a new object which eventually can be used for constructing three-point function. And I will show you how following similar logic than the one that was so much successful here will allow us to go very close to what could be the final answer, which we don't know yet, and which eventually will fit in this very recent and powerful quantum spectral curve. Okay, so the lesson from the cylinder, so this is the same as with Romuald, so I will try to be fast. So we are computing the scaling dimension, and we think about it as we put the theory on the cylinder, or we conformally map the sphere to the cylinder, and we want to know what are the finite volume eigenstate. But this is a very difficult problem. This is a spin chain on top. So choosing this string on the cylinder is like fixing a gauge. It's like choosing this particular vacuum. The length, the number of adjoint fields here is exactly the same as the length of the cylinder. And then to make the story a bit more spicy and interesting, we switch on some other complex scalar field which start moving on this frame of Z and start interacting and so on, and give rise to complicated and non-trivial energies. So again, as I started to say, so solving this problem is very difficult because it's finite volume. So physics in finite volume or equivalently at finite temperature are typically difficult problem. And so the first things that we can do to try to simplify is to first consider a very large volume where we can neglect these finite size effects that Romuald mentioned, which are making finite volume so hard. And the way I want to think about it is that we are essentially cut opening the cylinder along some dashed line. Okay? And what we are getting is now two extra edges, which are these dash edges, which are a bit of an off-shell construct because here everything is ending on something physical that you can think as being on the boundary of LES, and it is fixed on these nice BMN operators. But here this guy actually wants to float around. They want to probe LES in all possible ways, which means that strictly speaking they are not totally physical boundary, but this off-shellness is very mild and is totally under control at large length. Okay? So as we will see, the prescription for eventually gluing back these two edges together or getting rid of this kind of off-shellness, if you allow me this wording, will be to precisely allow this guy to fluctuate, which will mean summing over all possible excitation of this edge. Okay? And due to the periodicity of the problem, we will put a state here, we will put the complex conjugate here for identification, and we will sum over all possible states. But prior to get there, we want now that we have this nice, flat, and infinite dimensional background, we want to understand the physics. And this physics was understood a long time ago by Basso. So we have some excitation which fall into some nice bifundamental representation of the symmetry group that the BMN preserve, and which takes the form of a left and right PSU2/2, which is extended by some abelian charges. Okay? So this extension is very nice because it also includes automatically the energy in the story. So we not only have some isotopic rotations that transform boson into fermions and so on, as we naturally expect in n equal to 4 super-ion Mills, but we also have this central charge that want to be part of the story and that automatically give us the energy. And what is even nicer is that this symmetry happens to be extremely powerful, as shown by Basso, the S matrix, meaning the fundamental excitation, the fundamental, observable between two incoming patterns is factorized into left and right mode, okay, up to a scalar factor. And each one of these factors, the left or right part, are totally fixed by the symmetry. So this is a rather unique feature. Typically, even for integrable system, we don't have such a powerful consequence of the symmetry. It's only when we take Young-Baxter equation, which express the fact that free particle scattering is factorized, that we can eventually fix this matrix part if you want totally. So here, this Basso symmetry is powerful enough to totally fix this guy, which at the end of the day automatically satisfy Young-Baxter, so hint at the fact that the theory wants to be interpreted as an integrable field theory. Then there is this scalar factor. There is a nice story attached to it, which can be fixed by using this crossing transformation that Romuald mentioned. So in the end, as I said, symmetry is so powerful that we find the complete solution. Here I'm just showing you the solution. It's a non-relativistic background, so the solution is a bit complicated. It's not parameterized by usual hyperbolic rapidities. We have this fancy beta rapidity and the Joukowsky map of it. But in the end, once you get used a little bit to it, you appreciate the result, which is totally explicit as a function of the momentum and the coupling. And similarly, for the scattering phase, by using this crossing equation proposed by Yannick, you can entirely fix the expression. Okay? And at this stage, you already did a lot of work because you essentially find all the infrared information, and you can try to move forward and solve the problems that you care about, which is not this a bit of shell problem where things are infinite dimensional, infinitely extended, but the one in finite volume. And the starting point, as I said, is that you want to trace over all the degrees of freedom here. So you have to consider this theory, which is living in this channel, which is orthogonal to the real channel you started with, and which is obtained by doing what you can call a double weak rotation. Okay, so a transformation which exchanges the role of sigma and tau on the worldsheet, and which ends up being just an analytic continuation. So you can, with all the information that we have on this H, we can do an analytic continuation and get all the information we want over for this mirror channel. Okay? And then what we're instructed to do is to essentially sum over all these states. So the asymptotic description I spent time to describe just correspond to picking the vacuum for this H. Okay? So things are infinitely far away, and so things are projected on the vacuum. But then when we want to take into account this so-called wrapping correction, this finite size effect, this virtual effect, we need to allow also for the exchange of this mirror magnon, and we can have one or two and more. And as you might guess, they are more and more suppressed as the length is large. Okay, so they are typically exponentially small, where E is the typical energy of this mirror theory. And at recoupling, they turn into high loop results, which in many cases are so small that we cannot even probe it using perturbation theory. Okay. So in this particular case, we actually know much better than that. We know how to carry out this sum explicitly and even resum it into this so-called TBE equation. There is this nice trick by Zamolodchikov. And so we have a much better description of the final object. And at the end of the day, if you even go further and work hard, you will find, like Kazakov and collaborator did, we will find that there is an even nicer formulation, which is this quantum spectral curve, which makes the symmetry, the full symmetry, not the one which is preserved by BMN, but the full PSU 2,2/4 manifest, and which essentially erase all these intermediate steps, but which are still behind and which we can use whenever we need. And this is what I want to do now. I want to try to import as much information as I can from this philosophy and this explicit result to the 3-point function. So in the case of the 3-point function, we deal with a sphere with 3 punctures, and the dual picture is this famous pair of pants that we have seen. And the question now is, how do we actually simplify this object? So this object is even more complicated than the one we had before. It has even more cycle, so we can have wrapping in all possible ways, and there can even be new effects that we cannot immediately see in this picture, and that we want to make more manifest. So we want to, as in the case of the cylinder, we want to kind of put this object on a plane. You could say that it is already on the plane because it's a sphere, but we really want to put it on a plane from the integrability point of view by removing all the length in the story and just looking at what stands behind a totally naked object. Okay? And the cutting procedure that we are proposing is closely related to the one that Romuald introduced, except that we go a bit further and we cut everywhere. Okay? So essentially, we take a sword and we slice our object into two. And what we find is that this 3-point function can be thought as being 2 hexagons on top of each other. So the hexagon, each one of the hexagons is made out of 3 real segments, which are taken out of the spin chain, and 3 mirror channels, which only appear after doing this cutting procedure. So the philosophy behind it, it was a kind of a motivation for us, even though it's not okay, it's not clear why we should do that, but is that closed string is a kind of open string square in disguise, and that open string square without open string square can be much easier in the case where the boundary of the open string are very, very far away. Okay? And the slogan, if you turn it into our language, is that the pair of palms should be thought as an hexagon square. So when is this description good? Well, as I say, it is good when we don't have contribution. Well, sorry, I should not say good because I think it's an exact description. But when is this description becoming much more tractable? It is becoming more tractable when we manage to get rid of this off-shell effect, okay? All this finite volume pollution that are making the physics harder. And here we see that we have new effects. So on top of the usual wrapping that will still be there because we have this cycle, we can go around, we have that our two hexagons can now start debate or discuss with each other by exchanging particles. So of course they can leave one separated from the other by the vacuum, but when we start having one particle here, it's essentially telling us that there is an excitation which is created by this hexagon, which here I depict by the kind of center of mass of the hexagon, which will go and stretch all the way to the other side. Okay? So this is a new effect that we have to take into account, and the idea is that the asymptotic description will be good or under control only if we can make sure sorry, that these three distances here are large. Sorry. Okay? And this will automatically include that wrapping are small because they are obviously longer propagating. The particles which are going around are obviously propagating over a bigger length than this one. So these are sort of half wrappings. These are new effects that we want to get rid of. So we can also have confirmation and a kind of more quantitative estimate of when this picture apply if we go to the dual picture in terms of the spin chain. Thank you. Then we don't have the worldsheet, but we have this weak contraction. So we are picking three operators. They have a given number of hydrogen fields, and we are considering this case where they can connect to each other in this setup. So here we see one of our hexagon, which is just this big object, and the center of mass is nowhere, but it's surrounded by this splitting vertex, which is a characteristic. And the other hexagon that we don't see is actually at infinity, if you want, and it's related to the fact that this point is also a nearest neighbor of that one, and similarly here and here. So we have another hexagon whose end are here, and which will go around like that. Okay? And so the distance that I was referring to, this distance that the particle, this mirror particle, can propagate through, are just accounted by this number of line of scalar propagator here, which are stretching between two pair of operators. Okay? And we can be very explicit here. We can compute this bridge, and they are directly given in terms of the length of each operator. So the claim is that if these lengths are large, the free length in the problem are large, then wrapping effect at recoupling are of order g to the power of this length, and so they can be neglected as soon as large. Okay? So here we notice that it is important that all the bridges are large. In fact, if I wanted to make contact with the Romuald description, I will presumably have to remove one of these bridge, which means in our picture that we are putting the two hexagons on top of each other, and so it's a sort of short distance limit, which obviously cannot be done without including a lot of virtual effect into account. Okay. So that was essentially for the vacuum. If you think that we are just taking some BMN states here, there are no excitation. So what does it mean to cut things in terms of hexagon when we have a particle? Well, it just means split the wave function. So imagine for simplicity that I have on one of my string, spin chain, I have two magnons. So what happens if I cut my object into two? Well, it depends where I'm cutting. I might end up cutting in such a way that I have two magnons on one hexagon and nothing on the other one, or I can have one on the first and one on the other, and so on. And as you might guess, we need to take into account all these configurations that correspond to all the possible ways of splitting the spin chain. And this splitting comes with some weight, which take into account the relative phase difference between each configuration. So for instance, I can go there, starting from this point, by just shifting this U2 through the bridge that connect these two hexagons. And this way, I pick up a phase, which is a propagation. Okay? I'm taking the particle through some trip of length L, so I pay a phase. Similarly, if I want to move U1 to the second hexagon, I would first have to scatter through U2, and so I will also pick an S matrix. Okay? But the recipe is pretty clear, and it only involves information that we already have, which is S matrix, momenta, and so on. Okay? The only thing that we have to do is to keep in mind that we need to perform this sum. So here is a summary. I'm roughly halfway. I think I have 5 more minutes. But if you bring this back home, I would be happy. So the summary of our picture is that to compute the 3-point function, we need to split the object into two. To do this splitting properly or gluing back properly, we need to integrate over everything that can happen with identification on the mirror edge. And we need to sum over all the possible way of splitting our wave function on the physical edge. And what is nice about it is that now we reduce the problem down to a more elementary object, which is to give meaning to this amplitude, where there are no lengths anymore. Okay? So it's just an object that looks like usual space-time, except that it has 3 asymptotic regions, okay, which are connected to each other. And this is the hexagon, which once dressed by some excitation becomes a form factor. Okay? So to simplify, actually, we can do the same kind of trick that Romuald did, which is we can imagine, so if I want to carry out this sum explicitly, I will have to take into account all possible decorations. There will be stuff all over the place. So what I can do is I can use this move that allows me to bring everything on one edge, and then I simplify a bit my object. Then we end up with this creation form factor with everybody on one edge. And if it helps a little bit, we can also introduce this hexagon vertex, which is like a bra, which can be contracted with 3 spin chain states. Okay? So now what this object is doing is just taking all these indices, which are the usual indices that describe an asymptotic excitation on top of a given edge, and we need to find how this edge wants to contract all these indices together. So how do we do this? Meaning, how do we fix this hexagon form factor? We use the symmetry of the problem. And the symmetry are extremely easy to find because here we are considering a 3-point function. So we are picking 3 operators, which are to start with BMN operator, so BPS operator. So we can imagine picking the first one to be trace of Z, the second one trace of Z bar, the complex conjugate. And then we have to take the third one that can connect to both. That's why I put both Z and Z bar. And because I want it to be BPS, this is real, so I need an imaginary part, so I need to use another scalar, complex scalar. Thank you. Okay? And this way I get this kind of field which fall into a family of correlator which have been studied. In particular, there is this nice paper, which is this twisted translated field. So these are all the same, but you think that when you move your operator from here to here, you translate it, and at the same time you perform some rotation such that this trace Z becomes this trace Z tilde. Okay? So what are the symmetry of this configuration, which is like our ground state? This is easy to find also. We are fixing 3 points. So from Lorentz, we just get an O3, which is rotation around this line. And we are fixing 3 scalars, 3 real scalars out of 6. So we have also an O3 from the R symmetry group. What is nice about it, thanks to this translation, rotation things, that we also preserve some supercharges, which are some combination of usual supercharge and superboost. And as you see, it mixes left and right. In fact, the full generator combined into one PSU2/2 that you can think of as being the diagonal subgroup of the original group that we started with. Okay, this group of symmetry of BMN. So instead of rotating left and right, now we are forced to rotate left and right simultaneously. And this is extremely powerful. For instance, it immediately fixes the 1-point form factor. So if you imagine putting one magnon only, which means one left and one right guy, you can do the algebra and see that imposing that the vertex is annihilated by the diagonal symmetry immediately give you a notion of invariant inner product with respect to this diagonal subgroup, which allows us to connect these 2 guys. Okay? If you pick a particular choice for the twisting and so on, it just means that when you have a boson, you get 1 epsilon and so on. Okay? So we get our fundamental contraction, and we can immediately go then to 2 particles and ask ourselves whether the symmetry is still as powerful as it was. And the answer is yes. So here we see the same magic as for the S matrix, as what was found by Bizert, which is that when we split our stuff into left and right, and then we ask ourselves what happened now from the supersymmetry point of view, we can think of the left as transforming like a particle from the PSU to left, and the right as transforming like an antiparticle from the point of view of this diagonal subgroup. Okay? And because the intertwiner is unique, we fix our object uniquely up to a scalar part. Okay? Thank you. Now we can move on and conjecture that this nice description actually generalizes to any n particle. And our claim is that if you want now to compute n particle form factor, you just split left and right as before. You scatter the left part, and eventually you contract it with the right part. Okay? And because the scattering is factorizable, we know how 3 particles scatter together. It's just a pairwise product. And so we immediately get an ansatz for n particle. Okay? So what remains to be done is to fix this scalar factor. I have to speed up, I'm sorry. So I have to impose this extra constraint that Romuald mentioned with like this Watson equations that action on the S matrix of the object, or the crossing condition, and so on. And if you combine this, believe me, it's possible to find a solution for this scalar factor. Okay? It's not unique, but it is very likely to be true. So now we can combine everything together into a prediction for the 3-point function. For simplicity, I consider this operator where we have 2 BPS and 1 non-BPS, like Tracy with some derivatives. These are nice operators that people like a lot. Okay? And the answer is just given, I square it for simplicity, it's just given by our hexagon amplitudes that I will detail up to an overall normalization. So this is the same factor as Romuald mentioned, which has to do with difference of normalization between infinite and finite volume. Okay? And this hexagon is just the sum of our partition of our objects that we just find, which is this 1/h. Okay? And at this stage, we are done up to finite size effect. If we want to take into account finite size effect, we have to take into account this virtual effect. Here I'm just sketching what happened at leading order when we put just one particle on each channel. So one particle here, vacuum, vacuum here, which means this guy, or the rotation of it. And then we have to carry out some integration, because now we have to carry out some integration. We have to take into account all the momenta here that can flow, and we pick up this extra contribution. So when does it affect the result? In the simplest possible case, for instance, I just want to show you some concrete expression, some concrete number to conclude. So I take small operators such that we can see this finite size effect at a very low loop order. So for the simplest case, where the length of the operator is 2 for every one, the relevant contribution comes from this opposite channel here and start at 2 loops. Okay, so you do the algebra using our expression, you find that this guy starts at 2 loops. If you make the bridge a bit bigger, then of course you are delaying the effect in this channel, which will only appear at 3 loops. Okay? The asymptotic part is the same in both cases, because the asymptotic parts only care about what is happening at the top here, it does not know about the length here, so it is the same. So the two results should start differing at 2 loops. Okay? And at 2 loops, we should see that the asymptotic description is valid for this guy, but breaks down here. So we extract data, from 4-point function. I have to be fast. And here are the results that we get. So here's the result for the long bridge, the one with 2 guys at the bottom. This is the result for the short bridge. We see that indeed they are the same up to 1 loop. All this number you might not see, but they are exactly the same. And they start differing precisely at 2 loops. And in particular, this guy is still rational, which hints that it is simpler, while these guys start developing some zeta of 3. And then you use our formula for the asymptotic description. You find perfect agreement here up to 2 loops as expected. And after taking into account this wrapping effect, you produce the zeta of 3 out of these integrals that I have flashed, and you find agreement here also. So here's my conclusion. So I presented you a strategy for computing structure constant, which is to cut open a pair of pants into 2 hexagons. And eventually, once you're done with solving the problem with your hexagons, which we believe we did to some extent, comes the question of gluing back this hexagon together consistently. Okay? And I have shown you what are our loop conjecture for these hexagons. So there are many things that we to do. One of them is to check whether this gluing procedure is complete, if we are not missing anything, whether we can resum it. Here we can play with strong coupling, because strong coupling has this nice feature that it gives us the answer as a minimal surface in ADS, for which everything can be computed using integrability, but it's a classical problem. And it is automatically resumming infinitely many of this effect, because the classical description does not care about your artificial separation between real and virtual effect. It just gives you the full answer in a particular way. So here we have a lot of data which will allow us to test our conjecture. We would like also to make contact with this string field vertex that Romuald described, which from our point of view we interpret as an extremal correlator. So this is what happened when one of the bridges in the middle disappears because the length becomes small. So the natural picture that we are getting is a picture of an octagon, and we do expect that this octagon should have some relationship with what Romuald discussed, but we don't have much. We don't have much to say at the moment on how to bootstrap this object. And eventually, there are many open questions that also waits to be answered. Thank you very much.
Questions or comments?
So there's this expectation that if you have a non-protected operator that then, as you move the coupling constant, and it becomes degenerate with the double trace.
Yeah.
Its 3-point function should have some pole.
Yeah. Yeah, it's a very good question. So the only thing that I can tell you right now is that this effect is totally non-perturbative from the lambda point of view. It's like trying to make the anomalous dimension becomes 2. So you need some finite value of lambda. You cannot study it. So what we can see is that if you look at this integral, that looks nice. Okay, well, fine. You see that it secretly depends on the anomalous dimension. And when you start getting too close to one of these points where things should diverge, actually the integrals start diverging as well. Okay. So this is just a single particle contribution to this integral. So there is a question of whether multi-particle contribution can kill this divergence, whether this divergence is physical, whatever. This we don't know, but we start to see some evidence that this 3-point function might, even though it can be very well defined, might blow up or diverge when the value of the coupling cross some threshold, which correspond to these double traces. But it's so much non-perturbative that it's very hard to access from this description at the moment.
Other questions or comments? I don't see any, so let's thank again Basso. And I guess that. Oh,
Yes, a brief announcement. I'd like to invite all of you to the reception, actually, which is right where you had your tea, and also the poster session, and hopefully you will see all the posters diligently and express your interest in what all these people have done. Thank you. 7:30? I would think so. Back to the hotel. Yes, yeah, but I don't know the time.